Okay, yeah, recording seems to be started. Okay, so we just looked at stability. Hopefully you can see, I assume you can see my screen with boundary value problems. So this is another chapter in the notes. Now this is quite a short chapter. I'm not going to spend too long going over this. It's just essentially sort of applications of our ODE solvers to solve a different type of problem. So up until now we've looked at what's called initial value problems, where you have your ODE, you have your domain, and you have your initial solution, and you solve for the rest of the domain. And what we're going to be looking at is what's called a boundary value problem, or BVP for short, which is when you've got your initial value problem. In addition, you have the solution at the upper bound of your domain. So this was so we know what y0 is. That's our initial solution for y at t min. But a boundary value problem means we have our solution of y at t max. It's called a boundary value problem because these are the solutions at the boundaries. Now, with boundary value problems, you could have a problem which has been specified. It might have a unique solution, just one solution, or it might have infinitely many solutions, or no solutions at all. So this is something we have to consider. So, for example, we got a simple ODE, first order ODE, y dash plus y equals 0. And we can calculate, or we can determine the solution to this quite easily by integration. So we have some constant, c1, times the cosine of t, plus another constant, c2, times the sine of t. So we're going to look at, we're going to consider 3 different cases for this ODE. Or boundary value problem. So the first, we're going to consider a domain that extends from 0 to pi over 6 with boundary values of 0 at the lower bound and 1 at the upper bound. So for each boundary, what I've done is I've written out the solution. So the solution at the lower bound when t is equal to 0 was 0 equals c1 times cos t plus c2 times sine t. So cos of 0 is 1, sine of 0 is 0, so therefore 0 must be equal to c1. And do the same for the upper bound. Okay, we got our solution is 1, and our t was pi over 6. Okay, so cos pi over 6 is root 3 over 2, sine pi over 6 is a half. Okay, now because from the first equation c1 must be 0, so this first term here is just 0. So we have 1 equals a half c2, so therefore c2 must be equal to 2. And plug the c1 and c2 back into this solution, and we have the general, or one unique solution, 2 multiplied by sine t. So that is a case where we have a single unique solution. What about if we have the case when our range is between 0 and pi? So do the same thing again. So when t is 0, we see that c1 is still 0, but cos of pi is minus 1, sine of pi is 0, so we got 0 equals minus c1. So we don't know, we've got no way of knowing what the value of c2 is. So c2 can take any value, and that boundary value problem has an infinite number of solutions. Okay, the final case we're going to look at is when our range is from 0 to 2 pi. Do the same thing again. So c1 is still 0, cos of 2 pi is 1, sine of 2 pi is 0, so we got 1 equals c1. But this contradicts the first equation, which said c1 is equal to 0. So therefore, this boundary value problem does not have a solution. So we got a case where we have a unique solution, a case with an infinite number, and a case with no solution. So that's the first thing to sort of consider. Now, for linear ODEs, it's possible to actually determine whether a boundary value problem has a solution or has a unique solution. So if we have a linear boundary value problem of the form, so we've got a second order ODE, pt is some function of t multiplied by y dash, qt multiplied by y plus RT. Now, if PT, QT and RT satisfy these two conditions, then you have a unique solution. So if they're all continuous on the range, so continuous means we can draw the graph of these functions without taking your pen off the paper. And QT is positive within our range. Okay, so for example, here we have y double dash equals tq plus 5 times y plus sine t. Okay, so in this case, we don't have any y dashes, so pt must be 0. Our coefficient of y is t cubed plus 5, and we also have the function sine t, which is rt. Now these are all continuous on our range 0 to 1. So in other words, we can draw these. So pt would just be a horizontal line at 0, at y equals 0, and we've got a cubic, and we've also got a sine function. So they're all continuous. Now qt is positive in our range. It's actually qt is never less than 5 in the range which we're looking at, so therefore it must be positive. So these two conditions are satisfied. So this BVP has a unique solution. Okay, so once we've established we have a unique solution, now we're going to have a look at two different methods for solving a boundary value problem. And the first method is called the shooting method. Now, just sort of imagine, right, you're an archer shooting at a target, and you shoot your first arrow, and your arrow is slightly to the left of the bullseye. So your natural instinct would be to, well, I'm going to aim a bit to the right this time. And you aim a bit to the right, you shoot your arrow again, and you're a bit to the right of the bullseye. So then you're sort of left a bit, you know, and you're refining your aim. So hopefully after a few arrows that you've shot at a target, you're getting closer to the bullseye. And this is the kind of premise behind the shooting method. So what we do is we split our boundary value problem. So for example, let's see the boundary value problem from equation 1. We split it into two first order ODEs. So that's just standard practice when applying numerical methods. Okay, so we have these two ODEs now. So from the boundary value problem, yes, from the earlier, from this one, we know what our initial value is of y, but we do not know what our initial value is of y dash. Okay, so going back to where I was talking about the shooting method, so we know our initial value of our first equation here. We do not know what the initial value is of y2. So what we do is we simply guess it. So we guess what our initial value is for y2, and then apply our methods to solve it. And then we see how close our solution for y1, which remember y1 is equal to y, how close our solution of y1 is to the upper boundary solution. So if it's and depending whether it's higher or lower than what we wanted, which is the solution at the upper boundary, we adjust our guess of our initial value for y2. And it's called the shooting method because of the analogy with an archer shooting at a target. Okay, so let's have a look at an example. Here we've got a 2-point boundary value problem. Okay, second order ODE, got a domain. The solution at the lower boundary is 1, the solution at the upper boundary is 2. So that's what we're aiming for. So we're aiming for our solution for y at the upper boundary to be 2. And we split this into a system of two first order ODEs. Okay, we know that our initial value for y1 is 1, and we're going to guess, and we use s for our guess value for y2. So what we've done in this code, which is just below, is I've used 3 different guess values for s. So I'm using a guess value of 1 to start with, then I'm going to change it to 2, then I'm going to change it to 1.5. And I'm going to use the Euler method to solve the initial value problems. As we saw with the stability, when I talked about the stability, the function Euler is defined right at the bottom, okay, because MATLAB functions in MATLAB have to be defined at the bottom unless they're inline functions. Okay, you can see I've got another one for the second order undercutter, which I'll use in a minute. Okay, right, so back up. Where were we? Here. Okay, so define our ODE function. So we have a system, and this is what you'll have to do for the assessment. So a big sort of klaxon should fire in your head now. It's like, we're solving a system. So in the coursework assignment, I'm asking you to solve a system as well. So this is an inline function definition. So we have y1 and y2. So we've got two equations, and the right-hand side of our two equations, the first one is just y2, and the second element for our output of this function f is y1 plus y2. Okay, so we define our domain. BVPs, that's a new vector. It's essentially what are our boundary solutions. So at the lower boundary it should be 1 and the upper boundary is 2. I've just noticed I've got a 0 there, so I'm just going to change that. Okay. Guess values were 1, 2 and 1.5. So I've got a vector S of guess values. So what I'm going to do is I'm going to loop through the vector and calculate the Euler method for each guess value. And I'm going to use a constant step length of 0.2. So I've used a for loop here to loop through the 3 guess values. Okay, invoke the Euler method. So our the Euler method. So this is our initial solutions for y at t equals 0. So the boundary value of the first element of the BVPs array and our guess value there, that's 1. What I want to do is I want to be able to output the table of solutions, and I want to be able to save them. So hence what I've done there. And output solution table, that just you can see down here what it does. So if you run that, actually I'm going to run it again because I did change it slightly, didn't I? Okay. That's changed it a bit too much. What I'm going to do is I'm going to do a bit of cheat. I'm going to put that boundary value back to 0, and I'm just going to quickly do a sneaky edit and put that there. So I'm using a solution at the lower bound at 0, just because that's what I based my analysis on. Okay, so I've got 3. This code here is outputted 3 solutions. So the first solution was a guess value of 1, which is that first row of y2, and we solved it, and y1 is our solution. So at the upper bound we have a solution of 1.5856. Okay, we wanted that solution to be 2, so we're below, so we undershot the target. So the next guess value, I increased it from 1 to 2. So the first row of this table, the second table here, y2 is 2, and if we look at the upper bound solution in the y1 column for the second table, we have 3.1712. So that's overshot the target, which was 2. The third guess value we looked at was 1.5. So that's just split the difference between the first 2. And if we check the solution at the upper boundary, we get 2.3784. Okay, so that's, it's still above it, so we can continue. Let's say the next one could be 1.25, and then we'd hopefully get closer. Try that. So if I add another guess value of 1.25, and this time I'm going to increase the loop to 4. So if I run that, let's see how much closer we got. Okay, oh, actually that's not bad. Okay, so the guess value of 1.25 gave us an upper bound solution of 1.982. So remember, we were aiming to get a value of 2, so we're actually quite close to that. So you can refine again. We're a bit under it. So if we increase our initial guess value, we would get closer. Okay, now I've also plotted the solution. Okay, so this is the first 3 guess value solution. So the black, I don't know if you can make out here, the black squares are our boundary values. So we have 0 at the lower boundary and 2 at the upper boundary. Our first guess value was s equals 1, so that's that lighter blue line. Actually, I should really change the colours. I've got Yeah, so I've got two different colours. It should be all right. So let's change that to blue. Let's change that to, say, green, just to make it clearer what we're looking at. Okay, so the first guess value was s equals 1. So it's the darker blue line. Okay, you can see we've undershot the target. So we changed the guess value to be 2, which is the green line, and we can see we've overshot our target. The next one was a guess value of 1.5, and with the red line, which we can see we're still overshot. Okay, what I could do is actually, we did it again for that increased. Let's yellow. Let's be cyan. Okay. Okay, so the cyan line. Okay, which is, ignore that, that's not the boundary values, it's just because I haven't updated the legend. But that one, you can see we're slightly underneath it, so it's better. So the shooting method is all about guessing and improving on that guess until you get your upper bound solution bang on. Okay, well, that can be done with trial and error, but that's not too efficient, and it's not too clever either. But what we can do is we can make use of route finding methods. So last year in numerical methods, you would have looked at the secant method, and the secant method is a method to find the root of a function. So if f of s is some function, okay, we're going to find the root of that function. Okay, i.e. the root is where it equals 0. So s is our guess value. So si here is a current guess value, and si minus 1 is some previous guess value. We have the value of the function f at those two guess values here as well, and this allows us to update our value of s. So s is a root of some function. So what we can do is we can define our function of being our solution at Tmax compared to what we're aiming for. So this is our numerical solution, and yn is what our upper boundary solution, what we're aiming for. Okay, so this gives us this code. Okay, so what we have here, this is using the secant method. So this is a function which I've defined at the bottom of the of this page, but I just talk it through here. So this uses whatever ODE solver you want. Okay, so as long as you calculate, or as long as you've defined your ODE solver, you can just use whatever ODE solver you want. F is your ODE function. T-span and B-vals we dealt with before, so that's your domain and your boundary values. H is your step length. And max iter, that's some number, because we don't want to iterate forever, so we need to stop sometime, so that's going to be your maximum number of iterations. Okay, so we need some initial guess values. Doesn't really matter what these are, as long as they're different. So I set them equal 1 and 2, and it doesn't matter what f0 is, it just needs to be non-zero, so I set that equal to 1. So we've got a for loop to loop through all your iterations. And this is where our ODE solver comes in. So whatever ODE solver you input into this function, it'll use. So for example, if this is Euler, it'll use the Euler function. Okay, so that calculates your solution using the current guess value, which is S1. So S0 is the previous guess value, S1 is the current guess value. So Si is essentially S1, and Si minus 1 is essentially S0. Then we calculate our f, which is our calculated solution at the end, or at the end of the array for y, minus our known solution at the upper boundary. This line here, that is our secant method to calculate our improved estimate, which is S2. And then we have to update S0, S1 and F0 for the next iteration. What we can also do is check for whether our two guess values, S1 is our current guess, or our new guess value, and S0 is our current guess value, because we've just updated them here. If they're within some small tolerance, we might as well stop iterating there. Okay, so this is example 3. Okay, so as you can see here, I'm using the Euler method. So if we're having a function as an input to another function, we have to precede that function name with @ Okay, that's just a MATLAB thing. So this invokes this function here to solve our boundary value problem using the ccount method, and this is our table of results. So you can see the ccount method decided on a optimum initial guess value for y2 of being 1.2614. Okay, which we used 1.25 earlier, and that was quite good, but so it's not, we weren't actually that far away. And you can see here it's accurate to within 10 to the minus 6. Okay, so we've got our initial value is 0, which is bang on, obviously, because we set that, and our upper boundary value solution is 2, which is what we're aiming for. Okay, so if I plot our solution and the boundary values, you can see we have our solution to our boundary value problem using the shooting method. What I should say is we're starting to deal with some accuracy. So in the shooting method, we've converged on 10 to the minus 6. So you would think, hang on, that's quite accurate. So therefore our solution to the boundary value problem would be accurate. But that's not so, because we're still only using the Euler method. It's still only a first order method. So if we compare that to the exact solution, which is given in here, so this is our exact solution. Okay, the red line is the exact solution, and you can see that's our Euler method solution. So you can see we still have some separation between our numerical and exact. Okay, so despite the ccount method giving values of our guess values to within 10 to the minus 6, it's the Euler method that's letting us down. So a simple solution to that is we can use the second order method, or a higher order method. In this case, I've chosen a second order method within our shooting method there. Okay, so you can see, okay, so that's our we've hit the upper bound target of 2, and this time the initial guess value was 1.0182. So again, if I plot that, you can see we got better. I mean, still, you know, a fourth order method, if I used RK4, that would have been better still, but you can see that's given us a solution. So always be wary about whenever you're sort of using sort of convergence on a method which isn't very accurate, you're just converging to an inaccurate solution. Okay, so that's the first method we've used to solve a boundary value problem. So that uses an ODE solver. I could have used an Adams method. I could have used any other ODE solver within that shooting method. What we're going to look at now is an algebraic approach for solving a boundary value problem. And this doesn't use any Runge-Kutta method at all. So this is finite difference method, similar to divided differences, but I know you've done with Leader. Okay, so what we do is we discretize the domain into a series of nodes. So these are very similar to, if I scroll back up, so these are similar to these things here. Okay, so at point, so if you had h is equal to 0.2, you'd have a series of nodes at every 0.2 along the domain. Okay, and we can use what we call finite difference approximations to approximate derivatives. Okay, so here we've got a table. So if we wanted to approximate a first order derivative, we have what's called a forward difference. Now these are just derived using the Taylor series. Okay, so a forward difference is a first order accurate approximation of y dash. So you take yi is your sort of current value of y plus 1 is your value of y at 1 step's time. Okay, so forward difference goes forward in y minus the current value over h, and we've also got a similar backward difference. So both of these are first order accurate, so they're fairly low order of accurate. We've got a central difference, which takes the node, I say node to the right, or the node forward along the number line t minus a node backward along the number line t, all divided by 2h. Now notice in the notes, but this denominator was h in the notes, it should be over 2h. And that's a second order accurate approximation of a first order derivative. And we have, if we want to approximate a second order derivative, we have this what's called a symmetric difference. Okay, these are all sort of, you can look these up in reference works. Okay, so if we want to use these to approximate the solution to a boundary value problem, it's quite simple. You just replace any derivatives in your ODE with finite difference approximations from here. So if we had this sort of 2-point boundary value problem, on the left we have a second order derivative, so I could replace that with the symmetric difference. Okay, and then if I replace it with a symmetric difference and then multiply both sides by h squared, so I'll have h squared times f of ty on the right and the numerator of our symmetric difference on the left. Now this is a linear system of n-1 equations, so big N, okay, so there's a number of nodes we have, so this is a linear system of n-1 equations. Now the values of the nodes at the upper and lower boundaries, so that's y0 and yn, are known. They're given here in our boundary value problem definition. So we can reduce this to a system of n-3 equations. So for the first equation, we'd have y0 minus 2y1 plus y2 would equal h squared times f of t1 y1. But since we know what y0 is, we take that over to the right hand side. So essentially what we're doing here with this system of equations is everything on the left is unknown, our y values, everything on the right is known. All of the equations in the middle for I goes from 2 to n-2 is we have 3 unknowns, yi minus 1, yi and yi plus 1. And for the last equation in the system, because we know what the value of yn is, we can subtract that from both sides. Okay, so we can express that as this matrix equation. Now notice we have a tridiagonal coefficient matrix. That's as a result of using our symmetric difference. Okay, so we'll get a tridiagonal coefficient matrix. So if we can solve this linear system, we can find the values of y1, y2, etc. And these are individual values. So let's say we were solving this using the finite difference method. This would be y0, that would be y1, y2, y3, y4, and y5. Okay, so I mentioned this was tridiagonal. That's useful because there's a very efficient method in which we can use to solve a tridiagonal system called the Thomas algorithm. And it's essentially Gaussian elimination applied to a tridiagonal coefficient matrix. If you want to see the derivation of this, you can click on this link here, which will take you to, I think, the Wikipedia page. Okay, so what we do is we do a forward sweep. So we have a tridiagonal matrix. The lower diagonal we call A. So in this case, our lower diagonal elements are all 1. The main diagonal elements we're going to call B's. So our main diagonal elements are -2. And our upper diagonal elements we call C's. And so again, we got upper diagonal of 1s. And we do a forward sweep. So we recalculate B and D by using this. So B1 would just be, B0 would just be 0. And then as we go up in I's, we just recalculate B. And we also do the same for D. Now D is the constant vector elements. Once we've done that for all I equals 1 to 2 to n, we do a back substitution. So xn is our solution. Okay, so you can see here this is the solution xn. So the solution of the last node is just d, or the last d divided by the last b, and the solution for all other nodes is given by this. Okay, so if we code that into MATLAB, we've got this code. I'm not going to worry too much about that. That's given below as well in the function section. You can have a look at that. Okay, so we have a forward sweep and we have a backward sweep. So let's have a look at an example. So this is example, I think it's 5.4 in the notes or something like that. So we have a second order, this is the same one from example 2 actually, second order boundary value problem. Now we replace our second order derivative with a symmetric difference. If I scroll back up, so we replace the second order with a symmetric difference. I'm going to replace the first order with a first order fold difference. So I'm going to select this first order fold difference to approximate y dash. So, okay. So if we do that, we end up with this equation. Multiply throughout by h squared. Okay, and do some algebraic simplification. And we have this sort of general form. Now the nodes adjacent to the lower and upper boundaries, since we know what the boundary values are, okay, so in this case the right hand side is just 0, but we know what y0 is. So for the nodes adjacent to, so node y1, okay, so we know what y0 is, so it's that's that yi minus 1 taken over to the right hand side. And similar at the upper bound, so we know what yn would be, so we have that y1 plus h times yn, we subtract that from both sides. So this gives us this matrix equation. Okay, so again it's tridiagonal, dependent upon h, so that's our step length, remember. So whatever h is, we'll have different values for our tridiagonal matrix. Okay, so if we use the Thomas algorithm to solve for that, okay, so I define my t-span, I define my boundary values, and again I'm using the same step length of 0.2 as we use with the shooting method. Discretize the domain, so calculate what your big N will be. So that's to do with your range of your domain divided by h plus 1. T is going to be equally spaced values from your lower bound for t to your upper bound in spaces of h. And I'm going to start off by initializing a solution array of all zeros. So y is going to be my solution array. The first element in y I'm going to set to the lower boundary value, and the last element in y I'm going to set to the upper boundary value. Okay, so now I need to define the a, b, and c. So the lower diagonal elements, the main diagonal elements, and the upper diagonal elements. Okay, so a was all ones, so I've just got n minus 2 lots of ones. B is h minus h squared minus 2, and I've multiplied that by an array of ones, so but then that gives me all of my b's, and I've done similar to c as well, so c just 1 minus h. Okay, do the same for d. So d was all zeros apart from the first and last element in d. So once I've got a, b, c, and d, I shove that into my Thomas algorithm, which I defined earlier, and that will solve for my unknown values of y. Okay, I've outputted that in a solution table, so you can see this is our finite difference solution. Okay, and that was our exact solution. So you can see that the values of the both boundaries actually match, and we've got a reasonable approximation. It's a lot easier to see via the by a plot. Okay, so that's our plot for our finite difference solution. Okay, we still have some separation. Okay, it's better than the Euler method, but we still have some separation. The reason why it's better than the Euler method is we used a second order approximation of y double dash, while Euler method only ever uses first order. Okay, so we have a solution. That's our finite difference method. I'm going to just talk a bit now about accuracy versus number of nodes. So we've seen that the finite difference method produces a reasonably accurate results. One way to improve the accuracy was use increase the number of nodes used, i.e. decrease the step length. So what I've done is I've got a different example here. So this is my ODE. I'm going to solve this using 51 and 501 nodes. So the reason why I'm using 51 instead of 50 is so that H is a nice sort of decimal. Okay, the range of my domain is 0 to 3, and I've got these boundary so at the lower boundary we have a solution of 1, and the upper boundary we've got a solution of 0. So I'm going to use forward and symmetric differences to approximate y dash and y double dash. So a forward difference is first order, and a symmetric difference is second order. Okay, there is a little bit of algebra involved here. So the node adjacent to the boundary, because we know what y0 is, okay, we take that from the left hand side to the right hand side. For all interior nodes in the middle, we have the 3 values, so yi minus 1, yi, and yi plus 1. And the node adjacent to the upper boundary, we know what the upper boundary node is, so I've taken that across. Okay, doing the same thing as before, but I'm going to solve for 51 and 501 nodes. So okay, so we discretize our domain. Because the number of nodes has changed, we're going to have a different value of h. Okay, so I discretize the domain. We define our A, B, C, and D arrays. Okay, and we solve that tridiagonal system. Okay, and I've saved the solutions. So T1 is a solution using 51 nodes, and T1Y1 is a solution using 51 nodes. T2Y2 is a solution using 501 nodes. Okay, and I've plotted them. So I'll leave you to have a look at this code another time. I mean, you don't need me to drone on about it. Okay, so this is the solution. So the blue line is the solution using 51 nodes, and the red line is the solution using 501 nodes. Now, it's not possible really to get an exact solution for this problem, but we assume that the red line with using more nodes would be closer to the exact solution than the blue line using fewer nodes. Okay, so you can see that's the red line would be, we're assuming the red line is closer. Okay, so we have some separation there. So that's kind of inaccurate. The using 51 nodes wasn't sufficient for an accurate result. Okay, what we can do to improve our accuracy is, instead of a first order approximation for our first order derivative, I'm going to use a second order approximation, which is the central difference formula. Okay, which is second order accurate. That was in the that table above. Okay, so this gives us a slightly different system, slightly different tridiagonal system. Okay, and I've altered the code above to change A, B, C, and D for our new system. Okay, so doing the same thing again. Here we've got the plot. Okay, so we've got a number of plots superimposed onto each other. So the blue line was the solution using the forward difference for the first order derivative with 51 nodes. The red line was the solution using the forward difference but with 501 nodes. There's a pale green line, which you can't really see because it's underneath a black line, just there, which is the solution using 51 nodes with our central difference, which is our second order approximation. And the black line is the same central difference using 501 nodes. So what I want you to notice here is there's very little difference between using 51 and 501 nodes with a central difference approximation. So what we can say is, using a more accurate second order central difference for the first order derivative means 51 nodes is sufficient. And there's no point using 501 nodes, you're just increasing the amount of work we have to do for it. Okay, so it's important that you can just reduce the step length between nodes, but it's much more effective to actually increase the order of accuracy of our approximation. Now, I realise I just talked about the finite difference method. That usually within another unit that would take, say, about 6 weeks of content. It's not something you really be. I'm not really going to sort of assess you in detail on this. So don't worry too much about having to follow all of this code and this. But what I want you to realize is that we can use a shooting method and an algebraic method, which is the finite difference for solving a boundary value problem. Okay, just to summarize what we just spoke about. So we got a 2-point boundary value problem. These are second order ODEs where we know what the solution are at the upper and lower boundaries. A boundary value problem can have a unique solution, an infinite number of solutions, or simply no solutions at all. So that's something to be aware of. The shooting method, essentially we guess the value of the second derivative at the lower bound of our domain, and then we alter that guess value depending on the solution at the upper bound. Okay, we can refine our guess values using the secant method. The finite difference method, what it does is it uses an algebraic approximation for derivatives, and that results in a tridiagonal linear system of equations which we can solve. Thomas algorithm is very efficient for solving tridiagonal linear systems. If you wanted to, by the way, if I go back up, go here, we could have used something like Gaussian elimination. Next week we'll be looking at some linear techniques for solving linear systems. So we don't have to use a Thomas algorithm, but it is by far the most efficient for a tridiagonal system. Okay, and if I scroll down, to a different method. So the higher the order of a method, the fewer nodes are required to achieve the same accuracy. So that sort of goes for any numerical approximation. The first sort of instinct really is, just use a smaller value for h to improve accuracy, but it's much more effective to actually use a more efficient, a higher order method than just to sort of what I call brute force or ignorance. So it's much better to be smarter about what you're, how you're solving the problem. Okay, so that's boundary value problems. There are some exercises here. What I would advise you do is you focus on the stability chapter and focus on those exercises, do those first, and do these ones afterwards. The reason I advise that is because in the coursework assignment, I've asked you to have a look at the stability of an explicit and implicit method, and I won't be asking you to solve boundary value problems in the coursework and in the exam either. Okay. Right, so I'm just about to stop the recording. Hopefully that has worked. I checked the earlier one